Okay, we are now on YouTube live streaming. So first, let me briefly introduce our speaker today. So today we are very happy to invite Dr. Rahul Kanaro from the Army Research Lab Open Campus. He's currently a postdoc in Department of Aerospace Engineering at the University of Maryland, College Park, where he's working on developing predictive capability to mitigate particulate deposition in rotorcraft engine and aid in the development of next generation functional thermal barrier coating. So Dr. Rahul Kanaro received his PhD in mechanical engineering from the University of Florida in 2020, so where he worked on model validation and hydrodynamics instabilities in high-speed dispersed multiphase flow at the center of compressible multiphase turbulence. So his primary research focus is the development of drug and heat transfer models for dispersed multiphase flow. His other research interests include the interfacial dynamics of non-Newtonian and complex fluids. And today, Dr. Rahul Kanaro will introduce his recent work on the spreading dynamics of Molten sand droplet. Rahul, please go ahead.
Thank you for that introduction, Zen. Hello, everyone. Thank you for attending this the seminar today. At the onset, I'd like to thank the organizers of this wonderful seminar series. For someone like me coming from a completely different background of dispersed multiphase flows, it has been a great exposure to the great research and very interesting work that's happening in the complex fluids and the soft matter side. And I've been fortunate and learning from some of the best in the field. So thank you for that. And for today, I will talk about our efforts towards understanding the damage caused by sand ingestion and the molten particulate matter in the gas turbine engines of rotorcrafts. I would also like to thank my collaborators. I've been fortunate to work with some of the absolute experts in the field of particle deposition in gas turbine engines and mesoscopic methods and reduced order modeling. So to give you guys a quick background on why we are doing this or why we are interested in this is that aircrafts in general, especially rotorcrafts, which operate in highly dusty environments, like the one you see in the picture on the right here, they suffer severe degradation due to the particulate matter that gets ingested into the gas turbine engines. And this is of very much an interest of the Army, since it regularly operates in such environments, and they want to understand the damage mechanisms that cause, because it greatly affects their mission readiness. Because once the engine is fully ingested, you have to ground the aircraft, take the engine apart, and do the maintenance. And there have also been reported cases of total engine failure. All the four engines of the commercial airlines, Boeing 747, have gone offline mid-flight because they flew through volcanic ash. So this is very much of an interest for the commercial side of air transport too. So what happens actually is that the larger particles, the larger sand particles, they get filtered out. So there are these particle separators at the inlet of the gas turbine, and they separate out larger particles. Anything greater than 80 microns doesn't get in. But these small particles, they go through the inlet, through the compressor, into the combustor, and they melt in the combustor, and they come out at very high velocities into the hot section of the turbine. Now you can't be, we can't increase the filter size at the inlet, because that would reduce, so that would cause a much bigger pressure loss, and that would reduce the efficiency. So we want to understand what the damage this molten sand causes on the hot section components. So what we know already is that these molten particles, they impact these hot section components. There is adhesion, which is followed by infiltration of the molten material, and once it has infiltrated, it solidifies and causes mechanical failure. Here you can see sand deposition in the turbine blades here, and this is in the vanes of the turbine, shown here. So how does this process actually happen? What are the failure mechanisms, and what are we interested in? So here on the right, I'm showing a schematic of the thermal barrier coating. So typically the thermal barrier coating, it protects the underlying substrate from the hot gases that are coming out from the combustor. The hot section operates in high pressure, high temperature regions. So here you can see at one end, we have the hot gas, that's the exhaust of the combustor. And at the very extreme, where the other end, we have the cooling air from the bleeds of the inlet, which pass through, and they're used to cool these surfaces. And in between these two gases, we have the thermal barrier coating. And this thermal barrier coating typically is applied in multiple layers. The very top layer is aptly referred to as the top coat, and it is typically manufactured using zirconium oxide, and it is slightly doped with yttrium. And as you can see, it is about 100 to 400 micrometers in thickness, and followed by that, we have 100 micron layer of bond coat. And after that is the superalloy substrate. That's the actual turbine grade. And in the blue here, we can see the temperature gradient across the blade. And this difference is about 300 to 400 degrees Celsius. And that is substantial, since that prevents the blade from melting, which protects the hot gas. The blade from the hot gas. And our interest for this research is looking at the top coat, because that is the first layer of attack, first layer of defense against the attack. And these top coats are typically porous because the engine goes through heating and cooling cycles, and we need to have the material respond to this thermal differences. So the porosity helps in expanding and contracting of the TBC. So the molten CMAS, when it deposits on this top coat, it affects the thermomechanical properties of the TBC. It alters the chemical conductivity, it alters the tensile or the yield strength of the material, and a bunch of other things. And the mechanical failure is especially the most damaging one, of course. It manifests as delamination, as you can see here in this cartoon here. These are these horizontal cracks. These are caused once the melt infiltrates into these top coat columns, and it solidifies. And once it solidifies, it has altered, it creates a composite material with the TBC, and it alters the mechanical properties, and it can't handle the stress anymore, and it just cracks. And it also suffers from these columnar cracks These are caused by the buckling of these columns. The same delamination is shown here on an SEM image on a similar top coat here in the literature. And for our research, we want to understand how the entire life cycle of the CMAS, ideally, on a TBC, so that we can develop or aid in the development of functionally graded TBCs. These are the next generation of TBCs that Army is pursuing. Since this is broadly a multi-scale phenomena, we have adopted a multi-scale modeling framework. We look at the turbulent transport of particles at a macro scale, and at a micro scale, we are concerned about the interfacial phenomena such as wettability or contact line dynamics and infiltration. And for this, we use particle-based methods, MDPD, the many body dissipative particle dynamics, especially. And for this talk, I'll not talk about the macro scale, our efforts on the macro scale, and because it's not very pertinent to the seminar here. I'll focus on the micro scale component, where we have looked at the spreading of molten sand droplet on our thermal barrier coating. So before we look at the molten drop spreading, I'll quickly recap the available literature and the scaling laws that we have for simpler fluids like water droplet or water glycerine mixers. So typically the spreading, it follows a power law. It is very well known, and it is characterized by two distinct regimes. A very fast inertial phase is followed by a slow viscous regime. And for low viscosity fluids, such as a pure water drop that is shown in this plot, the exponents, they scale as half, 0.5 in the inertial regime, and it goes as 1/10 in the viscous regime. And this 1/10 is the Tanner's law that we have. And these results are from the very well-known experiments from David Perez's group, where they first made the connection that a droplet spreading on a solid surface is very analogous to the coalescence of two identical droplets. On the same line, we have experimental evidence for high viscosity liquids. And here, the scaling laws are slightly different. It's not a pure power law anymore. This comes from theoretical considerations of Stokes flow. And we can see that it has a logarithmic correction along with a linear dependence on the time. But in experiments, what people have observed is that in the inertial regime, the spreading rate is not a constant. It varies between 0 and 1. And in the viscous regime, it again recovers the 110 or the 0.1 scaling given by the Tanner's law. And for CMAS, we have a very high, molten CMAS is very viscous, and it has very high surface tension. So compared to a water droplet, you can see it's about 3,600 times larger viscosity. So we asked the obvious question that do these spreading regimes hold for CMAS? And to help us in that direction, ARL conducted some really nice experiments where they looked at the spreading behavior of molten CMAS. And they compute the contact angle and a bunch of other things. And they looked at a wide variety of thermal barrier coatings. So what they do is they take sand, which is the AFRL2 sand. This is especially used to model the naturally occurring sand. So this is a model sand. They take the sand, they roll it up into a spherical ball. They put it in the furnace. fire up the furnace, heat it to 1260 Celsius, and let the sample undergo phase change and subsequently the spreading. So here you can see a movie of the spreading process. You see it shrinks because there are some volatile gases which evaporate upon heating. Let the movie play again, and you can see it has a very shallow contact angle, and this is very characteristic of CMAS on molten CMAS on thermal barrier coatings, and this has been observed by various other research groups. So here on the right, we have the evolution plot of the contact angle in the black and the sample temperature in the red. So as you can see, the temperature is slowly ramped up to the target temperature, and then it is held constant at the target temperature, which is 1260 Celsius. By the end of the experiment, they observe a final contact angle of about 30 degrees for this particular TBC, which is 7% yttrium stabilized zirconia. So it's the zirconium oxide based TBC. And to look at the spreading dynamics of this molten sand, we use the many body dissipative particle dynamics method, which is a multi-phase extension of the TPD. Here are the governing equations. Since this is particle based, we are in the Lagrangian frame of reference. The force has three components. It has the dissipative force, the stochastic random force, and the conservative force. The conservative force, the only difference between MDPD and DPD is we have the additional density dependent repulsive force, which makes the coexistence of these different phases possible. And these are all pretty much the standard MDPD method that is available in lamps that we have used for this work. And typically with these particle-based methods, especially with DPD or MDPD, the challenge is that we do not specify any physical properties of the system of our interest. Typically, these are computed from the simulations, and the other problem is how do we relate an MDPD system to a physical system? So to answer the first bullet here, compute the fluid properties, we resort to the standard practices of DPD to compute the viscosity, surface tension, and the equilibrium contact angle. So to compute the viscosity, we set up our doubly periodic Poiseuille flow. So the flow in this channel is going in one direction. The force is applied in one direction at the top half, and at the bottom half, it goes the other way. We let the system evolve, get it to the steady state, and then we fit the MDPD solution. To the MDPD solution, we fit the exact solution. And the free parameter in the fit is the kinematic viscosity. And that is how we compute kinematic viscosity. And to vary the viscosity of the system, we looked at various cutoff distances for the dissipative force. So RD represents the cutoff distance for the dissipative force. And here we can see how that changes, how viscosity changes for different RD. And the open star here represents the value that we have used for our simulation. And as you can see, the cutoff is a bit high, so that we can represent the molten sand. Next is the interfacial surface tension. This is an even simpler setup. It's just a periodic box of particles. We let it equilibrate for a few hundred time steps, and we compute the stress in this thin box of particles. The surface tension, the average surface tension, is plotted here as a function of the attraction parameter A in the conservative force. As you can see, we have looked at different values, and we use -40 for our case. Next up, we have looked at the equilibrium contact angles. So we wanted to stay as close as possible to the experimental data or the experimental evidence, which says that these drops spread rapidly and wet the TBC at a very high degree. So we only use 3 shallow contact angles, not so shallow, like 70, 55, and 39 degrees. And these are the parameters that we have obtained. And I want to highlight these 2 parameters here: the exponent on the kernel, the weighting kernel for the dissipative force, and the cutoff for the dissipative force. So we alter these so that we can get a high viscosity of the DPD, of the MDPD system. And the next question is, how do we relate the MDPD system to our physical system? For that, we use the standard approach in one of the standard approaches in literature, and we use reference length, mass, and time scales to do that. And we non-dimensionalize the number density, the surface tension, and the kinematic viscosity to get the appropriate mass, time, and length scales. And these depend on the physical properties of the system and the MDPD values obtained from these pre-processing simulations that we did. So finally, we have all that we need, and we carried out a few simulations to look at the spreading regimes and how the contact angle evolves over time for a molten sand droplet at a fixed temperature of 1260 Celsius. And here are the properties of the CMAS that we used. These properties are completely dependent on the mixture composition of CMAS, and we have used this excellent experimental reference to get our values. As you can see again, the viscosity is quite high, and so is the surface tension. And from our non-dimensionalization, the parameter mapping that we did, we obtained these reference units. And as far as the simulations go, we performed 5 simulations at different contact angles and different initial drop sizes. And when we look at the Ohnesorg number for this setup, it's quite high, clearly indicating that the flow is viscous dominated, which is pretty obvious. Here is a quick snapshot of the simulation. So we start with the spherical drop sitting close to the solid surface. And this is how the droplet evolves in time. It's probably the most simplest MDPD setup that you can do. So I'll go into the results that we have obtained. So here on these plots, these are both log-log plots. What I'm plotting is the contact radius, the spreading radius on the solid surface as a function of time. And in the left plot, we are looking at the effects of drop size, and on the right, we are looking at the effects of the equilibrium, the final equilibrium contact angle. And from these plots, we can clearly see there are 2 distinct regimes. We have this fast inertial regime here, and we have the slow dynamic of the viscous regime. So we recover. Even for CMAS spreading, it is characterized by these 2 distinct regimes. And as expected, we see that the smallest contact angle, the one with 39 degrees, it takes a very long time to reach equilibrium, and also that it has a very smooth transition between the two different regimes when compared to the other two contact angles that we use. Also, one other interesting thing to note is that the duration of the viscous regime for the smallest contact angle is much larger compared to the other two contact angles. So obviously we like to compute the slopes and these different regimes, and that's what we did. And before that, we non-dimensionalize our data using the viscous time scale given by this expression. And we see that for drops of different size, the data collapses. This is very much in agreement with experimental evidence for low viscosity fluids, and this is a very universal behavior. And we looked and we do a least square fit in the inertial regime and in the viscous regimes. We observed that the spreading rate is about 0.26. It's much lower than that for a pure water drop, of course. And in the viscous regime, we see it's very close to 0.1. As you can see on the right here, it's 0.12, it's 0.1. So it's around the ballpark of the Tanner's law. And on the right, where we have different contact angles, we don't see such a collapse. Again, this is expected. But what is interesting is that even at these different contact angles, the rate in the inertial regime is identical. I should say it's pretty close to 0.26 for all these three curves. It's between 0.26 and 0.275. So clearly the spreading is independent of the drop size or the equilibrium contact angle, especially in the inertial regime. Next, to see how we compare with the experiments, there is this really nice paper where they looked at volcanic ash from the volcano in Iceland. They did the same experiment, similar experiment as the ARL experiment that I showed. They looked at spreading of volcanic ash at isothermal conditions, and they report these following slopes shown in the right figure here. For the inertial regime, these are only for the inertial regime. And you can see these are somewhere between 0.26 and 0.28 throughout different temperatures. So that is in very good agreement with what we see in the inertial regime, which is about 0.26 for us. And this was a really nice confirmation. The one thing that I want to stress here is that the volcanic ash, it has a higher viscosity than sea mass, but the surface tension and the density are very identical. We've also looked at the drop height of sea mass, and we see that the transition is very smooth between the initial position and the final position. And we can compare this to a very low viscosity fluid to see how the impact of viscosity pretty much does on the spreading behavior. This is a low viscosity system which we set up based on a previous publication from George Kanedakis' group. Here we can see that the transition, so initially the drop spreads without any change in its height. This is very interesting because the driving mechanism here is the interface curvature at the liquid solid interface. And after a point, transitions and viscosity takes over, and we see these oscillations before it reaches equilibrium. This is very interesting at low viscosity. So at very high viscosity, we don't see that behavior because the capillary waves are damped in the drop. Next up, we looked at the spreading rate, the slope of these curves as a function of time and as a function of non-dimensional spreading. And for reference, we have used the experimental data of Eddy and co-authors. And this particular data point, which is shown in open circles, refers to the pure glycerin drop. So the viscosity is about 1 pascal per second. It's about 3 times lower than molten sea mass. So the numerical, the simulation data is shown in these other symbols for a particular contact angle, equilibrium contact angle. And on the right, what we have is a dashed line, which is given by this expression. And how do we obtain this expression? As we take a derivative of this expression, which is the theoretical spreading rate for a high viscosity liquid. And in their experiments, Eddy and co-authors, they found that the low viscosity drops follow this line very closely. And in their experiments, the lowest viscosity was like 20 or 30 millipascal seconds. So it's still quite viscous, but it's less viscous compared to molten sand. So they observed that for low viscosity fluids, the slope follows this line very closely, and you'll see some deviation as the viscosity increases. We do not capture this early behavior here, but at the very end we see that it has qualitatively the same downward slope with the expected theoretical value. Next, we also looked at the dynamic, how the contact angle evolves in the simulations here, showing the evolution for the different contact angles. It's very informative. We can see that initially the separation is very low, and once the partial wettability effects kick in, that's when we see the separation between these curves. Similarly, we have computed the contact line velocity of at the triple point. So we just take the time derivatives, and we look at that as a function of the contact angle. But instead of plotting it as the velocity itself, we can plot it in terms of reduced velocity or capillary number. And we have nice theory and a bunch of models to explain the dynamic contact angle behavior. And pretty much all of these models, they stem from Cox's theory, which gives us an expression of this sort, which relates the apparent contact angle that is observed to basically to the capillary number. And we do the same, but instead of Cox's model, we use Kistler's model, which is an empirical fit based on the experimental, a lot of experimental data. And interestingly, this also has the same functional form as the Cox model. So that's a very good thing for us. And we plot our data in these reduced velocity units as a function of capillary number. And we can see that there is a really good agreement between the model itself and what we see in the simulations. And this is again a very very promising result, and it shows that the wide applicability of Kistler's model, which is still valid for such high viscosity and high surface tension fluids. So that concludes the spreading process. Our results on the spreading process. We have submitted all these results to the Physical Review Fluids Journal, and it's currently under review. So this is a summary of what we've done. We have carried out MDPD simulations using very large viscosity to investigate the spreading dynamics of molten sand. And we have observed that it has the characteristic inertial and viscous regimes observed in other low viscosity fluids. We see that because of the high viscosity, the viscosity itself is the rate limiting process of the spreading, and the surface tension, it controls the spreading kinetics. The spreading coefficient in the inertial regime was lower as expected, but was in good agreement with experimental evidence of volcanic ash. And finally, we see a very good agreement between the theory and numerical results with respect to the dynamic contact angle evolution. And so that ends the spreading part of the talk. And I would also like to present some of the results on melt infiltration that we have been looking at recently. So as I said, these TBC surfaces, they're also porous. So it is very important for us to look at infiltration and understand how understand the dynamics of infiltration. And for that, as a first step, I've been looking at simpler geometries. These are isotropic rough surfaces of cylindrical pillars, and we adjust the spacing between the pillars to look at the parametric effect of spacing. We also have we can also look at different contact angles. Again, I use the same contact angles from my previous study. One interesting thing that we see is for the 70-degree contact angle, we see the final angle increase to 80 degrees. So there is a Cassie-Baxter type effect here, but we don't see that in the shallow contact angle of 39 degrees, because as you can see here, this is the top view of the same image. The spreading is very non-axisymmetric. These are very recent results. These are a month, less than a month old. And we are looking at, again, this is pretty much the same things that we looked on a smooth surface. We're looking at the spreading rates. We're looking at infiltration rates, which is of interest here. Here is a quick movie of this infiltration process. As you can see, the 39-degree contact angle, it infiltrates and spreads much faster compared to the larger contact angle. In the past, we have also looked at infiltration into what are known as feathery microstructures. These were fabricated by the German aerospace group, and to study the infiltration, we generated these idealized surfaces, and we use the image here to generate the MDPD wall. And this is a great feature of particle-based methods, which I'm a big fan of right now, coming from a continuum-based methods where meshing is a real pain. So generating these complex arbitrary structures is very easy. In MDPD, we have here two different configurations. We looked at different spacing between these feathery microstructures. And we looked at the infiltration depth as a function of time, and no surprises here. The narrow feather is shown to inhibit penetration. These are some of the things that we have worked in the past, and we are looking at it again now. And some I'd like to end this talk with some of our ideas for future work that are ongoing. So in the ARL experiment, they observed something interesting. So here I have the contact angle evolution for two different surfaces. So the red is the rough surface that we have seen in the movie, and in the black is the smooth surface. As you can see that from the roughness measure here, so it's very smooth. What we see is that the smooth surface has a smaller contact angle compared to a rough surface. And this trend goes against the Wenzel theory, which says that if you're a hydrophilic drop and you're on a rough surface, your contact angle will be much smaller. And there are some explanations as to why that's happening. One of them is that the sample preparation is not a standardized procedure. They just use their hands to roll it up into a sphere. But what I think is happening is melt infiltration. They have reported melt infiltration for some of these substrates. So I think that is probably what is causing. But there are other mechanisms like contact line pinning that can also happen on these TBCs. Here is a snapshot. Sorry, not a snapshot. This is the topological map of a small scanned region of this surface, the 7YSZ surface. And we used this height information. Basically, that's the roughness on the surface, and we generated the MDPD surface. And you can see it's a very random rough surface here. And we have looked at the initial stab at the problem. We have looked at spreading on this this surface. Here is a movie, but this starts at a very late time of the droplet spreading. And you can see the effect that these small structures have on the contact line motion. It's very regular spreading because it has pinning and depinning and other processes here. And the last thing that we're looking at is the non-isothermal spreading. All the results that I've shown up till this point are for an isothermal system, and we want to extend this to a non-isothermal system. We are working in that direction by combining the energy conserving DPD with the multi-phase DPD, with the many body DPD, to get what we have termed EMDPD. Because one of the drivers for that is that the viscosity of molten sand is highly temperature dependent. It's very sensitive to temperature. So when it penetrates through these porous structures, there is a temperature gradient, if you remember from the first image of TBC. And that temperature gradient increases the viscosity of the infiltrated fluid, and that's how it freezes and causes all kinds of damage. And that is what we are working on. We are currently in the process of validating our numerical method, and we hope to have some interesting results very soon. And with that, I would like to conclude my talk, and I'd like to thank everyone for their time. And I'll take any questions the audience has. Thank you.
Thank you, Rahul. Excellent work. And also you introduce a lot of possibility to do this in some future direction. I think it's very valuable for our audience. So if you have any question to Dr. Conner, you can unmute yourself and ask Dr. Conner directly. So anyone have Want to start with your question? Oh, Jiaoyan, I saw you, but cannot hear you.
So how about now?
Okay, now it's good.
Okay. Yeah, good morning. Hi, Rahul and Jen. So I would like to start by asking some questions. So as Jen mentioned, it is a very interesting talk with the emphasis to the DPD development and a possible future application to the very interesting material system. So I do have two questions. So first of all is about your core screening for the CMAS that you called the new material. CMAS, yes. So when you do the core screening, I'm wondering, say so for example, for one of your contact simulation, for your current simulation, what is the diameter of your droplet?
Yes. So in MDPD units, the drop sizes are 8 radii. So I'm talking in terms of radii. So it's 8, 10, and 12 unit.
8 and 12 unit. But in physical unit, what is the size?
And physically here are the sizes. So based on our non-dimensionalization, one unit length is about 17 micron. And these come out to be about hundreds of micron, basically.
Yeah, 0.1 millimeter.
0.1 millimeter.
Millimeter, yeah. But I noticed that in your experimental part, the diameter of the droplet is more like 6 to 10 millimeter. Yeah. So there is one order difference, like more than an order difference there, right?
Yes. So the problem with matching with the experiment is in the experiment they can't do a smaller sample, and in the simulations we try to keep the cost down and look at a slightly smaller system. But in the future we are planning to match these scales, these length scales in the experiment. Right now it was just a numerical consideration because we were concentrating on the dynamics, and we don't expect these dynamics to be affected by the size here.
Yeah.
And usually in the application, in the actual physical phenomena, the particles are even smaller. These are 10 to 50 micron in size.
Oh, really?
Yeah. So if I can show the very first slide. So typically these are smaller than 80 or 70 or 80 microns. Yeah.
But meanwhile, I'm just curious, can you so when you do the DPD core screening, could it be possible to just increase the say currently one of your DPDBs represent, I don't know, maybe couple of nanometer or micrometer. So when you try to use an even like crosser model, could it be possible to just push your current 0.1 micrometer droplet to like a 1 or 10 micrometer droplet?
Yeah.
So see any kind of challenge over there?
Yes, we have tried to do that in the past. And one way to do that, one way to increase or reduce our the length scale, which gives us the one-to-one correspondence, is to have very high viscosity in the DPD system. And to increase this viscosity, the best way is to increase the cutoff distance. I mean, the best way is to adjust the exponent, but you can only adjust it to a certain extent. And beyond that, we can increase the viscosity using the cutoff distance. And obviously, as you increase the cutoff distance, the computational cost goes up, right? So we made a compromise there that this is how much we want to spent, because the simulations that I'm showing here, they took a week to run.
So how many beads do you have in the system?
In these drops have about 16,000 DPD particles, I believe. Somewhere between 14,000 and 16,000. I don't remember exactly now. The number density is 6.75.
Okay, so the computational the limitation exists in the time scale instead of the length scale, right?
Yeah, I mean the time scale, I think this is reasonable for the drop sizes that we have here, because as I've shown in the results, we were able to capture the dynamic effects pretty well. But if we look at the experiments here, you look at the x-axis. This is in minutes. It takes about an hour for this experiment. So there is a clear distinction between the length and time scales of the experiment, the length and time scales of the actual physical process, and the length and time scales that we looked at in the simulation.
I see. And my second question, in fact, is about your dynamic contact angle calculation. So you do mention the setup for the static contact angle simulation, but for the dynamic, I'm just curious, how do you set up your simulation to measure the dynamic contact angle?
Yes, I should have explained that. Yeah. So to compute the contact angle, we basically do a curve fitting basically to the surface of the MDPD, to the surface of the water drop.
Yeah.
So we fit a sphere, an approximate sphere, to the interface particles.
Oh, the dynamics means the dynamic process of the.
Yes, it's just varying with time.
I was thinking, maybe the droplet is moving or something like that. Okay, I'm sorry about that.
Yeah, but I mean the droplet is it's spreading.
Yeah, it's spreading.
Yeah, and this is a 2D snapshot. But what we do is we fit a sphere on top of these particles and compute the contact angle here.
Yeah.
At every time.
I see. Yeah. Thank you very much for the further explanation. And
thank you for your question.
Very good work. Thank you.
Thank you.
Yeah, following Joanne's question about the time scale, what's the reason you have to run so long? It's because this is a very slow process. Or?
Okay. Yes. Then the process is very slow.
Okay.
And also I think it's also the cutoff distance was also an issue. I guess typically we use 1 or 0.75, and as you said, the dynamics are very slow.
So it's because the viscosity here is about more than 1,000 times larger than water, right?
Yes.
Then if you run the same spreading process, because the viscosity is so high, you need to run the time scale. Maybe it's also, you can see that the normalized time scale here is kind of proportional to the viscosity. So if you have a viscosity is 1,000 times larger, that means you want to run the time is also 1,000 times longer, right? So this make your simulation.
Yeah, that's a good point. Yeah.
Okay, so any other question? So Rahul, I have a question about the length of the viscous region. So in the knock-knock scale, you show there is a very clear initial region of the spreading, but the viscous region, you see the 0.1, the ratio of 0.1 part, and the slope is very, very short. So does this I know this slope does not change with the droplet size, because when you change the different size of your droplet, this curve collapse. But what happens if you change the viscosity? For no viscosity fluid, you still have very short viscous region, or is different?
So that depends on the final equilibrium contact angle. Essentially, if we look at the experimental data here, for very low viscous drops, the transition is very sharp. And if you have, and that aspect is actually covered in this paper by Howard Stone's group, where they looked at different contact angles, and the time it spends in the viscous region depends on the final equilibrium contact angle. The shallower the contact angle, the more time it takes compared to a very high, like a super hydrophobic surface. It immediately reaches equilibrium. It reaches equilibrium pretty fast.
Okay. So you mentioned maybe you change the contact angle to change the length of the spreading the viscous region, right? But cannot change by droplet size or viscosity part.
Exactly.
Okay.
Yes, that's what we need. Yeah.
Okay. So any other questions?
Hey Jen, if we don't have other question, can I ask one
Sure.
more? Sorry about that. So as you mentioned at the end of your talk, so you are trying to develop EM DPD, right, to couple the energy DPD with many body DPD. So for this case, I'm just curious if it could be possible to rely on this EM DPD to capture the phase transformation, like from liquid to vapor phase?
So I don't think we can do the phase change with EM DPD because we have to be careful, right? When you undergo phase change, your pair distribution function also changes. So if you have solid, it's densely packed, and as you become a liquid or gas, it relaxes, right? So if we do not have that mechanism in EMDPD right now, but that is also our one of our future projects to look at phase change and also look at chemical reactions, because the molten drop reacts chemically with the TPC. So
right.
It's down the line.
I see. But then, do you have any comment on the phase transformation for?
Yeah, for the phase change, I think if you consider the energy equation coupled with the momentum equation, for the solid to liquid transition, maybe it's very easy to handle in MDPD. But if you consider the liquid to vapor phase transition, this may be harder because the density change maybe is the ratio maybe 1 to 1,000. 1 to 1,000 means you need to generate another phase. The density is 1,000 times smaller, and there's a different strategy you can do. For example, you can split the particle, but this kind of thing you need keep splitting and merge to merging, and this is a very challenging technical part, how you can do the splitting smoothly at the interface. Another strategy maybe we can do is you can try to change the interaction between particle. I'm not sure if it's doable, but because in the phase change, the latent heat, the energy equation and the energy change is significant. So how you can make everything physical process during the phase transition is captured, it's another open question. How you can, of course, if you just want to make the liquid become vapor, and it's for you can use a lot of trick to do that. But the problem is how you can capture the physics during the phase transition process. Is you should consider carefully how to do that. You cannot just use some tricks. Okay, I just do splitting, and also I just change the interaction to generate the phase. It's not the story. The story is how you can represent the physics during the phase transition process.
Yeah.
One trick that I've seen in literature is, and for liquid to vapor phase, is they just delete particles. Once the particle becomes, based on the latent heat, if it's vapor, they just delete particle from the system.
But how you can, because you know, if you do the liquid to vapor transition, the system will absorb heat, a lot of heat. So if you just delete the particle, you did not solve the problem.
Yeah.
You have to consider how the energy is changing in the system.
Yeah, thank you very much, Rahul and Jen, for sharing the good insight and possible future direction. Thank you.
Thanks, Joya, for the very good question. It's kind of currently it's an open question. Nobody knows how to do that.
Right.
Okay, if no more question, we will end here. Thanks again, Rahul, for your very interesting talk.
Yeah, thanks for
being here, Rahul.
Yeah, bye.
Bye-bye.